So I just go to the second slide. No, it's not going. Second slide, you can see that table of contents.
Yes, yes, I can see.
And if I write red curve, can you see that?
Yes, yes, yes.
Okay, fine.
Okay, perfect.
Thank you.
So, okay, fine. So you already introduced in the morning, so you can start, Palash.
Okay, thank you very much, Professor Sairam. So in this session, can you hear me properly? Is the sound is okay for all of you from the participants?
Sir. Yes, sir.
Okay, perfectly fine.
Yes, sir.
Okay, so today and in this session, I'll talk about the simple linear regression, and which is one of the fundamental concept in statistics, as well as in, if you prefer to call it machine learning or data science. And here the idea is to find the association between two variables, and I will explain that. And the way I will start with some motivation so that you can connect them clearly. And in between, because there are a lot of participants, so I'll stop in between to take a few questions. I will not be able to take many questions because time is limited here, but I will take some from you. And at the end, I will make the floor for open discussion where you can put your questions directly to me, so we'll able to solve jointly. Okay, so I am an assistant professor at the Department of Mathematics, and I'm also associated with the School of Health Science and Technology, and I'm also an adjunct assistant professor at the Center for Quantitative Medicines, Duke NUS Medical School, Singapore. So before joining here, I was there for about more than 5 years. So now to give you a perspective, so my background in statistics, and you see that I'm already associated with health science and technology and also work in a medical school. So the knowledge in statistics is become so fundamental right now in this way. So every aspect you need this kind of background. And in next 10 years, I will expect that the knowledge in basic statistics will become like whatever like the basic calculations or the basic programming language. So right now, for example, if you are working as a professional, so everybody expect that you should be able to write something on the Microsoft Word, and you should be able to handle something about the Excel. So similarly, the basic statistical knowledge will be become in such that in 10 years, people will expect that you know the basic things. So let's start with the simple linear regression today. And I'm sure a lot of you have already heard about this, but for some it may be new. So I'll start assuming that nobody know anything about this one. So first I'll start with the motivating example here, and so that you can connect where things are going on. And then I will introduce the simple linear regressions, or the SLR, and how to fit an analysis. So by fitting means a data set is given to you, and then there are certain parameters. By parameters, I mean that unknown quantities. How do you estimate those things? By estimation, I mean that you need to find a suitable value. When I said suitable, means that you need to have defined some kind of criteria by which that is suitable to you. And then analysis, once you have the fitted, then what are the interpretation? So you have a data, you are fitting model. So remember, these are all statistical tools. When you have a tool, that means that you have estimates. Now, what is the use of that tool with respect to the data? What new information you are bringing on the plate after you fit the simple linear regression model? So we'll discuss on that means fitting and also the analysis of that. Then I'll generally talk about the how to attack the data analysis model fitting problem. So remember that. So you have a data, you have basic science problem. That is a research question behind that. You are having one particular model that I am talking about, simple linear regression model. But model is not important. It is important what the basic research question that you are going to answer. It may happen that data that you have is not suitable for your model, then your model is of no use. So model is one tool, one part of the bigger picture, but the main thing is that what is your data, what is your research questions, and what kind of questions you are trying to answer that. Okay, so we'll talk about a lot of things, and I'll give you a lot of motivation how to handle all those things. And remember one thing, that statistics is not mathematics. So being known a mathematical model is not, always important if you do not have the sufficient information how the data is collected. So if you have a same data set, but how it was collected, depending on that, your analysis and interpretation will change. Okay. So here we'll talk about again what are the different steps of predictive modeling using the simple linear regression. So I will explain with respect to simple linear regression model, but these steps are actually important for any type of models that you can think of or you will learn later on. Okay. So here I'll talk about the research question. So as I pointed out, that a research question is very, very important to us, and we all need to answer what is going on there. And so first I will start with one of the research questions. Here it is very simple research questions. What is the impact of attending classes on the student final marks? So my intuition or my objective is to understand whether classes attending has any impact on the final marks. And why do I want to know that? Because then I can encourage my students that, okay, look, so those who attending class have higher marks or something like that. So, but it may happen the data we have may not be sufficient. So that is a separate question. So we have a very small data here. So let's start with one real data. By real data means we have actually one data that is collected from IITG, so that you can feel. So a lot of time you will start with data that you may not feel, but this is the data that you can typically connect with. So what you are seeing here is a scatter plot. So this might be a new term for you. So this scatter plot means that you have a x variable here in the x-axis, and we have a y variable y in the y-axis. And we just plot the points of like this kind of points. Xi, Yi. Okay. So whatever I am writing is visible to you, right? Can one of you just confirm?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Okay, perfectly
Yes, sir.
fine.
Yes, sir.
Okay, fine. So I will plot all those points. So here we have this many of students, and all these points are already plotted there. And here our objective is to trying to find that the attending class. So what is my x-axis here? Number of days attended. So around 40 classes are there typically in a semester, and these are the marks from here to here. Okay. Now when you plot the scatter plot of the number of days attended here and the marks obtained by the students in a data science course in IITG. Okay. Now what do you see that these are the points on the graph, and if you look closely, that you will see or you will sense that there is an increasing trend kind of things. I can see some kind of increasing trend here. So as students are taking more and more classes, they are more prone to having more marks. For example, there is a cluster here. So these students obtain the highest marks, and look at that, they almost attended more than 38 classes. So here in this region, one of them attended all the classes. So that means that whoever obtained more than 70 marks have attended most of the classes. But there are some exceptional also. Look at these students. They are not attending most of the less than 32 classes, but still getting some amount of marks, but not as high as that. And there are these students which is attending most of the classes, around 38 or something like that, but still getting something around 45 marks or something like that. But what I want as from a model, so model, whenever I do statistical model, my intention is not individual. My intention is what is happening in population. So from this scatter plot, you can say that in population, that is population of that particular class, I can see that if you attend the class, then there is a chance of getting higher marks. But it may happen, there are a lot of examples, as I pointed out, those are not falling into the average criteria that you can think of. So, but those are things will be data there because it is a real data, those problems will be there. But in model, what I want, or in a regression model, what do you want? I want a linear relationship. Okay, but in practice, there will be a lot of points which will be here, which will be here, will be here. So that's not a problem. Now, the fundamental question is here, we will do a regression analysis to the above data to find the answer of that attending classes on student final marks. But the question is that whether using regression appropriate here. This question you should always ask. So if you have a data, you are trying to fit any model, not only regression model or any other model, first thing you want to ask that, is this the right model for it? Because it's not like that you have a hammer and everything looks like a nail, not something like that. So is the model, and model depends on some kind of assumptions, whether those assumptions are made or not, we'll give light on that. So let's go to that idea. So as of now, you have a scatter plot and you have plotted the data, and you can see that there is some kind of increasing trend with respect to days attended and the marks obtained. Okay, so now intuitively, our objective is to choose a straight line. Okay, yeah, straight line. So that is also called the regression line that minimize the error. What is that error? I'll come into that. And this is called the residual. Okay, so now the why fit the regression line? So you should ask always questions, more ask questions. Asking question means that whenever you are trying to fit something or doing some kind of statistical analysis, you need to ask questions to yourself again and again, because model is something that you are trying to infer knowledge, and there are a lot of possibilities that inference may be wrong. So you need to check that again and again. So here I am talking about the regression line, but why not a curve there? I can fit a curve, and that could be a better one. Now the question is that, can regression fit be a curve also? So we are talking about the straight line here, but I'm asking you again question, the regression fit can be a curve also. And what is the residual? So I'll answer all these questions. So as of now, suppose you know the regression, then we have fitted the line for you, and this blue line is the line that we observe. And it is the minimizing all kind of errors, that is we call the residual here. Okay, so let's check that. Now here we call again learning a new term. Earlier you have, so let's go back. So you have already learned one thing, scatter plot, that is a new term if you have not heard about that one. And then we are talking about the residual. Okay. And now again, we are talking about the diagnostic plots. Okay, I will explain everything to you. So now fitting a regression line to a given data, that given data means we are talking about the data that means related to IITG data science based on several assumptions. Okay, so those assumptions should be checked before and after fitting the regression line. So that means some assumptions you can check by looking at the data, that means before the analysis, and some, once you feed the data, then you can check whether those assumptions are made or not. So you have to check all those assumptions to make sure that everything is working fine. But literally saying that, and sometimes you will not be able to check all the assumptions as perfectly as you want, because we are living in a real world situation, and a lot of things will not be falling exactly as you want, but we have to settle down where, depending on what kind of job we are working on. Say, for example, what we mean by this statement, suppose you are trying to find out this relationship. Here, whether your model fitting is good or not does not matter at all. Okay, so if you predict something wrong in these attendant classes and final marks, nothing will go wrong. But suppose you are talking about the effect of a, say for example, a particular parts of a rocket which you are launching from a ISRO. So suppose you are working in a ISRO and they are launching a rocket, and your job is to fit a regression line in some part, and that is analyzing the effect of a particular parts. Now, if your model is wrong there, the entire rocket launching can be affected, and millions of the dollars will be wasted there. So you need to understand that what kind of thing you are working on, depending on your assumptions or validity, the results, all those interpretations will be changed. So these are very important, where you are working on and what you are working on. If your risk is minimum, then you can sometimes avoid that. Okay, assumptions are not that good, but in practice, it is fine enough. But for the rocket science, it's not fine enough. It may be a very vague sentence. I'll come into that later on. Okay, so some assumptions can be checked by the diagnostic plots, and these are the diagnostic for diagnostic plots. I will come into that later with respect to specific examples. As of now, you just assume that these are the diagnostic plots. So if these assumptions are not made, the regression model may not be appropriate. So you have a data and you are trying to fit a regression model, but once you check those assumptions are not made, it's better not to fit the regression model there. There are a lot of other statistical models that you can think of, or you can play with that, whether those models are fitting enough or not. Okay, so here, this is a long story, the importance of graphing data before analyzing it. So there are 4 graphs here, 1, 2, 3, and 4. So now my question to you, which graph do you think has the highest correlation and ideal for linear regression? Okay, you see this graph, and in this graph, this is the scatter plot and the draw a line.
X3.
Yes. Sorry?
X3 versus Y3.
Is it
X3
X3
versus
sir?
Y3. Okay, now this is interesting. So someone said X3 versus Y3 is more popular. Okay. Now, in
versus
all
Y3. First term. Okay.
So all the 4 graphs here, 4 graphs, mean of X is 9 and variance is 1. That means this graph, this graph, this graph, this graph. The X, that means here, 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 have the exactly same mean. That means average 9 and variance 11. And for the Y variable in all the 4 graphs have exactly mean of 7.5 and variance is 4.1. And the correlation coefficient between X and Y is exactly 0.816. That is quite high, 80% correlation. Now, see that these graphs are typically extremely different. So from this one to this one to this one, they're all extremely different to each other. But still we have exactly same average with respect to X and Y. And correlation in all the cases is 81. So this is called Anscombe graph. So he's demonstrated in 1973 to demonstrate the importance of the graphing data before analyzing it. Now here somebody told that this is the right graph, but look at that. Here the actual observation something like that, but because of that, this line is pulled towards it. Okay. And this here, what we observe for a given X, that is maybe 8 or something like that, you have exactly same, different values of Y. Okay. And here we have a nonlinear relationship, basically. But here, this is the perfect one. What I see that these points are having some increasing trend there, and there, when I'm fitting this line, the points are randomly distributed towards the upper half and the lower half of that particular line. So this is the best graph that I can think of among these 4 graphs, which is most important for the linear regressions or simple linear regression that we see. So if we fit the regression line in each case, all of it is exactly same regression line, that is Y equal to 3 plus 0.5x. So this is, by the way, to give you an idea that what you see is not always correct. And things are pretty simple here because you have one dimension, that's only one X variable. But when you have more variables, things will become much complicated. But this one idea, so that you need to plot things before you can go further to check whether everything is working fine or not. Okay, so now we'll talk about in more detail. So now you have sufficient idea about in which direction I'm going on. So here we'll talk about the linear models and meaning of linearity. Okay, so when I teach classes, so whenever we are saying something, try to understand that what does it mean by the term itself, simple linear regression. So regression is the concept, and we are talking about linear. What does it mean by that linear? And we are talking in the simple things. That means we are talking about only one variable. We'll come into that. But let's understand what does the linear means in linear models. Okay, so regression is one of the linear models. There are lots of other linear models. So a linear model is linear in parameters. This is very important, and this concept, a lot of even well-known people who are working in statistics or data science, they sometimes miss that. Understand that, but not in necessarily in the X. So by linear, I mean that linear in parameter, beta or alpha, whatever the parameter be, but it is linear in parameter, but not necessarily in the X. Okay. So for example, if I consider this model y equal to beta naught plus beta 1 x and beta 2 x square, so this is a linear model because it is linear in parameter beta, even though there is a term called x square. Okay, so you remember when I'm talking about the whether linear model, I mean linear regressions can be curved. So this, if you plot this curve in something like that, it could be something like that depending on what kind of parameter beta 2 you have. So but that means that linear regression not only be a straight line, it can be curved also. So this might be some of you who already studied linear regression may not be familiar, but yes, linear regression can be curved also. It may not be the straight line, but if you drop that one, so if you consider just y equal to beta naught plus beta 1x, yes, that is a straight line. But if you add that term x square here, beta 2 x square, so then now things become a curve. Okay, but it's still a linear model because it is a linear in parameter. Very crude way to check that, it's in additive, and the power of the beta is like 1. Beta here 1 1. Sorry.
Is it curvilinear called?
Curve, you can say that, but I don't approve that language. So I will say that curve or something like that. But if you wish to call that, I have not seen that kind of things, at least in statistical literature. Okay.
Sir, I have one more question.
Yes.
What about the interaction thing, like say if we have the product of beta 1 and beta 2, would it be a linear or non-linear?
Product of beta 1 and beta 2 means?
Pardon me, sir?
I don't understand what is the product of, you are saying that.
Sir, if we consider, say, if we have a term like beta 1 multiplied by beta 2, which usually happens in multiple linear regressions, say, wherein we examine the interaction in
tomorrow's class.
So, sir, will that be linear or non-linear?
So, are you saying that you are saying about this kind of things?
So beta 1 multiplied by beta 2 and then say x. Yes.
X square.
Yes. So this form.
So but why do you do that? You can replace this one like a beta star x.
Yes, sir. So then, sir, what a parameter is and how is it different from a normal variable? Because in terminology,
here you say that this is a linear model. So these kind of things are not recommended. You are saying beta 1 term will be like this one, right? Am I right? Yeah. So these here, so these parameters are called the non-identifiable. Okay, I will give example. So let me, you estimated this one as, say, for example, 12. Now, beta 1 can be 2 in 6 equal to 12. 3 into 4 is equal to 12. This is called non-identifiable. From this, you will not be able to identifiable this one. So, I mean, I don't know how do you get this one. There is no way you can do that. This is the wrong way to do that. You have to use this kind of things. Okay, I'll come to that, the interaction part tomorrow.
Right, sir. So I have one small question here at this point.
Yeah.
How do you call this beta 1 or beta 2 as parameters? So what a parameter is, and how is it different from a normal, say, constant?
Okay, I'll come into that. Let me finish this one because we have limited time. Okay, so here the second one, that y equal to beta naught plus beta 1 x to the power beta. Now this is a nonlinear model because it is not linear in beta. In another sense, in a very crude way, suppose here if you increase some value here, that will be directly in a linear increment of y. But here if you increase something, that will not be related linearly with respect to y. Okay, so here linearity is already done. Here we are talking about the some kind of transformation when the linearity is not there. For example, here we are having the outcome variable y, and this is our model beta naught x to the power beta 1. This is not a linear model. I can clearly see, you can clearly see. Okay, so now, but if you take a transformation, like I just take the log of fx or log of y here, then log of beta naught. So this beta 1 will be come out here, that is beta 1 log x. Okay. So, and if you don't like this as a linear model, just take the transformation like f star to be log of f, beta naught star equal to log of beta naught, and beta 1 star equal to beta 1, and similarly. So you have the familiar model of y equal to beta naught plus beta 1 x type of. So this is a linear model. Okay. So although linear model seems to be simple and restrictive, you can think of that you cannot do a lot of things out of that, but they can actually be quite flexible by transformation of the response and the predictors in terms of the, if you think of, so this kind of model can be useful in some cases, and when you convert that into a linear model, so things are becoming very easy to understand and easy to interpret. So as I already said that linear models are not just straight lines, they can be curved also. And I have also already provided one examples there. Okay. So these are some of the nonlinear models, and your job is to transform this model to a linear model. So I will just explain one of them, and rest of things you should be able to do by yourself. So for example, I am the easier one. This is the easier one. If you just take like 1 by y, that will be beta naught plus beta 1 x1 plus beta 2 x2. And then you just take y star is equal to 1 by y. Then it will become y star beta naught plus beta 1 x1 plus beta 2 x2. So that's a linear model. Similarly, your job will be to transform these two as a linear model. Think of your, I mean, a little bit. It's not very difficult, but if someone is starting just now, it could be a little bit worrisome, but you should be able to do that. Okay, now I'll explain all those things related to simple linear regression. So regression is a technique. Linear, you mean the linear in parameters, and simple here in the case that we are talking just about one predictor here. Okay, so that means P is the number of predictors in the multiple linear regression model that we'll talk about tomorrow. And in this case, that in case of multiple linear regression model, we'll have a P greater than equal to 1. Okay, but here we have a simple linear regression by y is equal to beta naught plus beta 1 x plus epsilon. So this is very interesting things. This epsilon is called the error term. Okay, so if you go back to your mathematics class in class 12, so you have already learned that y equal to mx plus c. Okay. So now this is basically, this part is y equal to, this is c, this is m, this is x. But what is interesting to make from the straight line to regression line, the addition of this error called epsilon. So statistician loves error. Without error, there is no job for me. So I'm adding error so that in real life, we are not perfect. So there will be error in everything you do. But our objective to whatever happening in real life to a mathematical formulation, but we also accept error, and our objective is to minimize that error as much as possible. Okay, so here y is the outcome variable, and X is the independent or predictor variable, and epsilon is the error term. And someone asked that what is the parameter? Okay, so parameter is beta naught and beta 1 here. Those are parameters. And the question was why it is different from some constant. So generally, so technically you can call this parameter as a constant also. So here, the beta naught and beta 1, they can take any values from within the real line, minus infinity to plus infinity. So these are special parameters or the constant that have some specific meaning with respect to regression line on any other models. Yes. Someone is saying something? Okay. So these are constant and which have specific meaning. Yes. I can hear you. Go ahead, please.
Hello, sir, can you hear me?
Yeah, go ahead. Yes, tell me.
Sir, in the nonlinear model, which you have explained in the 2 slides previously, sir, can you go to there?
Here? Hello?
Yes, sir. So
Yeah.
this one. Sir, you
Yes.
said that the function of X is somehow not affected directly by the betas. And that's why the model is non-linear.
Sum of X? Say that again.
Sir, you said that the exponent in the beta 2 in the nonlinear model, the beta 1, the exponent of beta 1 in the that is beta 2 in the nonlinear model. Sir, you said that it is not affecting directly Y. Sir, can you please just emphasize on that issue?
I didn't say that. So what I'm saying that suppose here in this case you increase the everything else is fixed. Okay.
Okay.
If you increase the values of beta 2 here, that is directly related to here. Okay.
Okay.
But here, if you increase the value of beta 2, that is dependent on X. Right? So say for example, if your X is very small, say for example 0.1, and your beta value is 3, then what is the change in Y? That will be something else compared to if your X is like 1, 3 to the power 3. You got my point?
Yes, sir. Yes, sir.
Okay. Yeah. So this is the simple linear regression model here, and equivalently we can write. So this is a generic model. I'm not talking about any observation right now. So here the model can be written as like yi equal to beta naught plus beta 1 xi plus epsilon. Okay, and here I denotes the observation number. Okay. So here I equal to 1 to n, that means that I have n number of observations, or if you are conducting a study, n number of patients and all those things. So y is the outcome that I want to see, and beta naught and beta 1 are the parameters. X is the input variable or output, or explanatory variables. In general, you will encounter a lot of times somebody came to you and fit a regression model with the questions, but from the data you are not clear what is X and what is Y. So then you need to ask the question, what is the cause and what is the effect? In that sense, very lucidly. So what is the effect that will be taken as Y, and what is the cause that will be taken as Xi in general? But there are a lot of other varieties and a lot of difficult problems. Those things are not valid at all. Okay, so these are the specific structure of y equal to beta naught plus beta 1 xi. Okay, now we'll talk about the assumptions. So there are 4 specific assumptions. So that first one is that errors epsilon I, they are uncorrelated to each other. they will not depend. So epsilon 1 will not depend epsilon 2, epsilon 2 will not depend epsilon 3, 4, and so on. So they are uncorrelated with each other. And this type of correlated errors is quite rampant in the case of the time series data, where you will have one lecture on time series also later on by Dr. Ganguly. So there we'll see that there is a typical relationship between the errors near to, when they are near to each other, they are similar to each other compared to when they are separated to each other, and that term is called the autocorrelation, but I will not discuss here. This is out of context here. So violation of these assumptions of errors is uncorrelated can lead to the misleading assessment of the strength of the regressions. So I need that my errors to be uncorrelated, and we'll have a way to check that one. Okay, and the expected value of the errors is 0. Okay, that means so this is the expectation sign, and if you are not familiar with this, just consider that this is the kind of theoretical counterpart of the average. Okay, so that is, yes.
Sir, can we merge those two assumptions, the first and the third one, that is the homoscedasticity and the errors are uncorrelated, to be termed as the errors are stationary?
You are going something in different way. The stationary, that all those things comes in the time series model, not in the regression model. Okay,
We
so
are
that
not
is
dealing.
Yes.
Sorry, just I wanted to add a point. We are not dealing with the stochastic processes, so we cannot talk about stationarity here. We are taking only one variable and several realizations of same variable, isn't it, sir?
Yeah. So here, and also I must say that, which I forgot, here y is a random variable and x is not a random variable, not stochastic. So when I calculate the expected value of y, then I will treat this x as a constant, but epsilon as a variable only. So this part will be treated as constant when I'm talking about the expected value, expectation calculation of the y. Okay. So the assumptions of homoscedasticity here, this is very important assumptions, and also known as the constant variance here. So given a specific value of this variable x to be small x, the variance of y to be sigma squared. This is same as the variance of epsilon is also sigma squared. That needs to be constant. And the last but not the least, the errors needs to be normally distributed. So these are the typical 4 assumptions that you need to check or you need to have to fit a linear regression model. Okay, so in nutshell, what we have there, errors epsilon are to be uncorrelated and expected value of epsilon to be 0 and variance of epsilon to be like sigma square for all the observation that you have I equal to 1 to n. Okay, so the last assumptions, that is assumption of normality of errors, is not necessary for the estimation, specifically the least square estimation. So that means if your objective is to estimate the parameters only, then it is the last assumption of normality is not required. So it is only required when you do the inference or the testing of hypothesis and confidence interval. So later on, you might want to test whether the coefficient beta 1 is equal to 0 against H1, the alternative hypothesis beta 1 not equal to 0. So if you want to check that kind of things, then only you need the assumptions of least square or assumption of normality, or in other words, assumptions of normality is playing here only, not in the estimation of the parameters. This is a very important point to remember. A lot of people just ignore that things, but this is the case. Okay. So here,
Sir,
now, yes.
I have a question. So,
Yeah,
what if these assumptions are not satisfied? Any of the assumption, or let's say all of the assumptions are not satisfied. So what we should do? that is clear that linear regression model, we cannot apply that model. Or you can say that that is not an appropriate model if any of these conditions or assumptions are not satisfied. So what we should do in that case?
No assumption is made, you should not do the regression.
Pardon, sir?
So if no assumption is made, you should not go for the regression.
So what we should do then, like we should not go for linear regression, or we cannot apply we cannot apply regression modeling, any of the regression modeling.
No, these are the basic. So if you are talking about the simple linear regression or multiple regression, if your errors are not uncorrelated and any of these violation, so there are other way to deal with that. But with the existing system, you will not be able to. I will discuss some of them. You can do some kind of transformation, and there are a lot of other area that you can venture out. But unfortunately, I will not be able to cover all those things here. So let's go there. Okay, so I will talk about the least square estimation here, but for some of you, this might be a little bit theoretical, but for the sake of completeness, you need to know that, so that I will go it very quickly. Okay, so goal here is we are talking about the least square estimation. Again, learn from the term. So we are talking about the estimation, we are talking about the least square. That means we are talking about the minimum of square of something. And here we have the square. Okay. So estimate beta naught and beta 1 by minimizing error. As I told you that error is very important part of statistician's life, and also for the linear regression. So we have some amount of error and we want to estimate parameters, and obvious choice is to minimize those kind of error in some sense. And one example could be square error. So this is one way. So one way of, or reasonable way, is to principle of least squares. There is no hard and fast rule. So you can think of any other kind of like objective function that you want to minimize, and you will still get some estimate. But with the experience of the last 200 years, it has been observed that the least square is the one of the best that we have. Okay. So here our objective function, I can write q beta naught and beta 1. What we are doing, so we have the error epsilon I. I am taking square of that. Taking square have a lot of mathematical advantage, and then I take the sum of all the error that I have. This is the quantity. And what is my epsilon? Epsilon is the difference between what is we have yi, the outcome variable, and the way I am modeling. So this is clear from like yi equal to beta naught plus beta 1 x1 or xi plus epsilon. So if you take that this quantity here, that is the error, and you are taking a square. So with respect to beta 1, beta naught, and beta 1. So if you differentiate these with respect to beta naught and beta 1 and equate to partial derivative to 0, so there are a lot of new concepts who are not familiar with this one, but I will not have time to explain all those things. You can go to any basic textbook of linear regression to check all those things. And if you ultimately differentiate all those things and equate to 0, you will have two normal equations. So these are called the normal equations. And finally, you will get this solution like that. So beta naught hat equal to y bar minus beta 1 hat x bar, and beta 1 hat is equal to sxy by sxx, which are denoted by these two quantities here. Okay, so this beta naught and beta 1, they are called the least square estimator, or LSE, and beta naught and of beta 1. So when I'm writing that beta naught hat, this is the estimate, and corresponding parameter is beta naught. So hat means the estimate. Okay, now this is unbiased or not. So this is again theoretical consideration. You can show that this is like beta naught hat is equal to beta naught. So this, when you take the expectation of the estimated value and that is equal to parameter, then it will call the unbiased, otherwise it is not. So it will be your homework to check that whether this beta naught and hat and beta 1 hat are unbiased estimated for beta naught. But if you are only interested in doing some kind of fitting regression models, you can ignore this one. These are a little bit theoretical, not too much, but still it is theoretical quantity that somebody may have some interest.
Sir, I have a question.
Yes.
So does this beta naught hat or beta 1 hat has a range or what?
Range of.
Do we have a range of these values so that we are taking their expected value as equal to the beta naught?
So what is the range of y here?
So, so since you wrote beta naught hat, since you wrote the average value of the beta naught hat is equal to beta naught, so therefore my question is that do we have a range of the beta naught hat values, or is it a single value?
So look at, so y is continuous here in general, right? So technically y can take any value minus infinity plus infinity, so does beta 1 and beta 1 also.
Right, sir?
Okay, so technically these are technically beta can take any values minus infinity to plus infinity. Now say for example, you are working with the data height versus weight. Okay, so your weight here and your beta naught and beta 1 height. Fine. Now you know that height cannot be negative. And similarly weight cannot be negative. Then you expect your beta naught has to be positive, and positive with some amount of, depending on data, it may happen. Suppose you are working in inches, so beta, you can expect beta naught to be around like, say for example, human weight maybe 30 inches or something like that, or 20 inches. So even though technically beta naught can take any values minus infinity or plus infinity, depending on where you are working, what kind of data you have, then it might have some restriction there. Otherwise, technically, it should not have any restriction. Makes sense to you?
So my question was slightly different.
What?
So my question was that do we have a distribution of beta naught or beta 1?
Yes, of course you have.
Since you are computing the expected value of the beta naught cap, I'm not talking about the beta naught or beta 1. My question pertains to the beta naught cap, beta naught hat, sorry, and then beta 1 hat. So do we have a distribution of the beta 1 hat, or is it a single value?
Let me ask you a question. Do you have any distribution for y?
So yes, so we have a distribution of y because it is given.
Do you have a distribution for x?
Yes, we do have, because it is given there.
What is the distribution for x?
Distribution of x is given there in the data. I mean, it could be.
In regression line, do you have any distribution for x?
Could not hear you, sir.
So in regression line, if you're talking about simple linear regression, do you have any distribution for x?
We do have distribution of x also, sir.
Well, so if distribution of x, then you need to have expectation of x. Have I talked about the expectation of x anytime?
No, sir. You only talked about the expectation of the error term.
Yeah. So here we do not consider x to be a random variable. Okay. So for my purpose of the linear regression, I will consider x as a constant variable kind of thing. So I don't calculate the expectation or any distribution. So you are talking about there is a distribution, and that is specifically normal distribution. From that normal distribution, you can find out the distribution of the y bar. From that, you can also find out the distribution of beta naught. Before that, you have to find that what is the distribution of beta 1 hat. So those distributions are already there. Okay, but I will not go into that much of theoretical details because I have very less time and I am already running out of time. Okay, that is a good question. So, but you can calculate the corresponding distributions actually, and those are very useful. Okay,
Sir, I have one question. Sir, we are calculating the parameters y difference, optimizing the ordinary least square errors. Right, we are differentiating with respect to beta naught and beta 1. Then why we are getting beta naught hat and beta 1 hat? We are differentiating with beta naught and beta 1. We should get beta naught, beta 1. Why we are getting beta naught hat and beta 1 hat?
So beta naught hat are the values.
So if we differentiate with respect to some variable, we will get the value of that variable. Like
let me explain. So you will get one expression for like this one. So you will get some expression of beta naught, or say for beta, you will get some expression. When you put all those values here, you will get a value of that, and that is called the estimate. So beta, so say for example, once I put all the values of beta naught, I will may get beta value of the beta naught 1.5. Okay, so beta naught is a parameter, and finally I will have some expression after you differentiate. You will have some expression when you put all the data from your values of the data like x bar and y bar. You will get some values, and that value is denoted by hat. Okay. So the now we'll come to that variance. So variance of beta naught. So I am already late, so I'll go a little bit fast, and I'll not take too much questions. So if we have time left, then we'll take questions. Okay. So because we have only around how much 40 minutes left, and we have a lot of slides to cover. But we'll have some time at the end. So this is the estimate. Someone asked that whether distribution, yes, beta naught hat and beta, they have the distribution, they have expected value, and they have the variance value. So do the least square based estimation problem different from the likelihood based estimation procedure? The answer is no, they are exactly same, but the mathematics required for that to establish, I will not go into that detail, but you can always check from in a specific book how they are coming. They are coming from the normal distribution explanation. Okay, so now this is very important, the geometrical interpretation of the least square. So here I'm talking about the minimizing of this quantity. Okay, so this is equivalent to minimizing the sum of square vertical distance between the actual y values and the any regression to be fitted. Let me explain very quickly. We are running out of time, but this is important. Okay, so these are the points. Okay, so we can see one increasing trend here, and let's assume that this is my fitted regression line. So what this quantity means actually, these are the vertical distance. So this is epsilon1, this is epsilon2, this is epsilon3. So basically what we are minimizing, all this error. And what does it mean? That means we are taking the error square, and so technically you can fit this line, that line, any line. So there are so many lines I can consider given a data. I will choose that line. So you can think of, we have a center and we are rotating the lines like this one, this one, this one. And I will stop there where I will get this error to be minimized. That line happens to be this line. So this is the geometrical interpretation for this simple linear regression, and this will maybe very useful to you to digest what is going on. Okay. So there are a few definitions that we must know before we go forward. So these are the fitted values. That means yi hat. So as you know that someone related to someone questions there. So these are the basically equation. And then when you observe value, this is denoted by some hat. Okay, so this is the fitted value when you have, so this is non-stochastic. I do not have to put hat. These are the estimated value. We will get the estimated value of the fitted value. Residuals is the difference between the observed. So this is my observed and this is my fitted value with hat. So this is the difference, and this is called the residuals. Okay, now the objective function evaluated at LAC, that is called the residual sum of square. This is RSS. This is very important. So when you put this value of beta naught and beta 1 here, this becomes the residual sum of square. Okay, so this is the residual, and you are taking a sum and of square of residuals. So that is the interpretation. And the residual variance and estimate of the model variance sigma square given by the RSS by n by 2. So there are very roughly, this is called the degrees of freedom, and the square root is called the residual sum of squares. So this n minus 2, this minus 2 is coming from that we have n number of observations, and we need to estimate 2 parameters there, and we are losing these 2 degrees of freedom due to estimate all those 2 parameters. So this is very roughly. intuitive explanation of the degrees of freedom here. Okay, so now this is by Box, one of the famous statistician. Essentially, all models are wrong, but some are useful. So we are trying to find out some of the useful model out of the all wrong models. So we also need to measure how well the model fits the data. Okay, and in this context, we'll use the residual sum of square or RSS, and whether this is an adequate measure or not, we have to check. So the coefficient of determination or R square is defined by these equations. This is 1 minus RSS by SYY. So SYY is total sum of square. This is the observed minus the average value. Okay, so intuitively, you can think of this is the maximum error I can think of, and now this is the error due to the residual sum of square. Okay, and in case of multiple correlation, I mean, these are called the multiple correlation coefficient in the context of the multiple linear regression that we'll talk about tomorrow. Okay, so this is a mathematical properties of this R square, and it can also be written as R square like. So if you do the calculation, you can easily come up with this SS reg by SSYY. So it can be says that this is the total proportion, that error that I can think of. Out of that variability, how much is explained by your model, that is the regression model that you have. And technically, you can show that it is bounded quantity with 0 to 1. So intuitively, that these are the two squares, so they cannot be negative. So they has to be lies between 0 and this is a superset of this one. So this quantity has to be less than this one. So its value to be 1. Now, a lot of statistical software, when you fit model, you can find out R square to be negative. Sometimes those are actually wrong. There are some other problems which is not defined properly well. And if you are talking about the least square estimation, the R square has to be lies between 0 to 1. But in practice, there are a lot of softwares. If you search internet, a lot of unauthorized sites, they claim that R square can be negative with some of the superficial examples. Those are not correct. Okay. So because of the above property, so you can think that percentage of variation explained by the model. Okay, so this model means that when you fit, so if your R square is like 0.8, I can say that the variability of the model is explained, 80% of the variability of the model explained by the regression line, or I should say that variability in your outcome variable, that is Y, 80% of that is explained by the model or the regression model. So higher R square value are desirable, but how high is how, that is a questionable and depend on the context. So if you are talking about the R square value, when I'm talking about the attending classes and marks, so there I say that 0.6 is a very good R square. But if you are talking about when ISRO sends a rocket to the space, and if you are talking about the R square value corresponding to some regression fitting model, then the R square value could be 0.9999, because I cannot afford any small amount of error when I'm dealing with such a high risk game. Okay. So that is basically tomorrow's part, multiple linear, but I will not discuss this tomorrow. In case of multiple linear regression, there is a concept called adjusted R square. So here, technically in R square, if you add more variable into the model, the R square value may get inflated. So to address that, the degrees of freedom of the corresponding structure has been divided by, and this quantity has been divided by the corresponding degrees of freedom, so that even if you add more predictors variable, this will be adjusted, and that's why the name came adjusted R square. Okay. I will take one quick questions if anyone have any question.
Sir, what is the degrees of freedom, the term which you used just now?
Okay, degrees of freedom. Very quickly, suppose you have a 3D structure, right? The x-axis, y-axis, z. So if you consider a point, very loosely you can think of your degrees of freedom is 3. Okay. Now, if you just get a plane out of there, so suppose that earlier you are saying that your point can be anywhere in the space. Now you are saying that your point has to be in a plane. Now, the moment you add more restriction here, there were 1 degree of freedom is reducing here. So here, when you are talking about the y here, so let's go back to that here. Here we are talking about. So here we have I equal to 1 to n observation. So you can think of that there are n-dimensional variability, very loose sense. Okay. Now the moment you are talking about the regression, you are restricting that you have to estimate those 2 parameters. Now that means you are just like you have a 3D point and then you are talking about 1 plane. So more restriction, then you will have less freedom, and there's 2 degrees of freedom just gone away. Okay, so in very loose sense, you can think about that how much free things we have right now. Okay, so here when I'm talking about the why I have n free things we have, but I'm also restricting y bar there. So there is a restriction like summation of yi, but there will be 1 restriction out of that. And that restriction is causing 1 degree of freedom, losing 1 degree of freedom. Similarly, this is coming from the residuals, and we have p parameters there. I'm losing 1 parameter there. P degrees of freedom there in minus p. That's things I can only explain to you. For others, you need to read that one. Okay, but degrees of freedom is a difficult concept to start with. But if you invest time, you'll be able to understand. Okay, so let's start with the diagnostics. So here, regression model depends on several assumptions. We know that, and these assumptions can be checked in regression diagnostics. We have to go very quickly. We are running out of time. So constant variance is there. So this is the fitted value, that means yi. This is the residual. And in this case, if the points are like in the randomly spreading here about the 0 and less than 0, then we expect no problem. If we have similar kind of things, we'll say that there might be problem of heteroscedasticity. And if we see this kind of structure or points distribution, then we can say that there is a problem of the non-constant variance. Okay, so this is the rough idea at what is going on. Okay, so if you have non-constant variance, and this can be addressed in 2 ways. Someone already asked that if you have some violation of assumptions, what can we do? So these are some possibilities that you can think of. Okay, so point 1, if you have some violation of the errors that can be corrected, then you can still go with the linear regression with the correction. But in some cases, you may not be able to correct all those things. So here, when you have non-constant variance, so you can go for the weighted least squares that I'm not going to discuss today. So it's the well-known technique, and it's so it transforms the model in such a way your error become the constant variance kind of things. So there is in case of linear regression, something like that, x transpose x. But in case of weighted least squares, you have this kind of things. Yeah. Okay, but I will not go into that details. It will take a lot of time. Okay, so alternatively, there could be some transformation of variable, considering the transformation response to hy when h is chosen such that the variance of hy is constant. So objective is to imply something so that our final product is the constant, or the variance of the outcome is constant. Okay, so let's go back again the simple linear regression model, yi equal to beta naught plus beta 1 xi plus epsilon naught. Okay. So here the variance of epsilon, that is the different. This is dependent on I. Earlier our variance of epsilon was like sigma square, that was constant, but here we have sigma I squared. That means that your variance of error is dependent on which observation we are talking about. So we have a non-constant variance, and how the parameter of the how to estimate the parameters using the least square. So we will not be able to cover everything, but here, if you observe that variance of y is equal to variance of epsilon is proportional to expected value of y square. Okay, then you can consider that this transformation log y transformation. Similarly, if you see that variance of expected variance of epsilon, that is the error, is proportional to the expected value of y, then you can think of square root of the transformation. But what you have to do in practice, you need to look at the plot of the residuals versus fleeted that we have already seen, and take a guess of the relationship, because these are very specific observations. But in practice, when you have the data is lot of messy, lot of problematic data that you can have. So you only thing you can do, you can guess and try that thing. If it is working fine, then it's okay. Otherwise, if your initial guess is wrong, you can always try to do another transformation. Okay, and look at that. We are changing SDY because we are talking about the SD in the same unit of the response. So whenever you do something, always think that what is the unit. So if you are comparing something response versus something else, then you should have the same unit that you are talking about for the both variables. Okay, so this is the QQ plot, or called the quantile plot. So this is assessed for the normality of the assumptions. So what I expect here, when you plot the QQ plot, I expect the lines to be as straight line as possible. Here, this is slightly there and side there, but in practice, this is still a good one. In ideal cases, hardly you will get all the points are belonging to a straight line, but this is fair enough for practical purpose. So, okay, so basically the idea is that plot of the quantile. So this is little bit theoretical, but I'll just state them and then I'll go to the next slide. So corresponding to the sorted residuals, sorted means that you have the residuals, n number of residuals, you sort that, minimum is the first and then maximum is the last. And then you plot against this phi inverse I by n plus 1. So this is the CDF, that is cumulative distribution function of normal distribution. To just look at how things are going from very simple to very complicated, because now you are dealing with something which really matters. So those things are a little bit complicated if you want to learn, but it is fine if you don't understand all these things, because what actually matters is the curve, normal QQ plot, whether they are plotting in the straight line or not. Histogram are not useful because of the problem of the bean size, that they can vary a lot depending on what type of bean size. So now we are talking about the unusual observations. So specifically, all of you must heard about the term outliers. So outlier means that observation that do not fit the model well, and there is concept called influential observation that change the fit of the model in a substantive manner. So this is the outliers and this is the influential observation. A point can be none, one or both, and above. Just to warn you that, so because of there is an outlier, you should not throw away any observation pointing out that, okay, this is outlier, so throw it away. So you as an analyst or as a statistician or as a data scientist, you should not do that. If you have an outlier, talk to the person who generated the data or who is the basic scientist, that is that an outlier? Because of the outlier, throughout a lot of happens that was a major problem in the ozonosphere layer. I do not have time to discuss that story. That was a fascinating story, but the bottom line is that you should not throw away the outliers because you think as a statistician to do so. You need to talk about the basic science. Oh, look, this is the outlier I came out, but if I throw out, does it make sense that it will be considered like outlier? For example, if you are talking about the blood pressure, and say, for example, for the time being, blood pressure can vary to 250. So if in your data you observe a blood pressure like 1000, anybody say this is an outlier because somebody just mistakenly input that variable to there. But if you observe BP to be like 300, this may not be outlier, even though rest of the data is far away from that. Because we know in some specific cases, this BP can be hit 300, and that may be actually signal to some specific rare disease or rare condition. So if you throw out that, you are just ignoring that and you are playing with the people's life. Be careful, do not throw away the outliers because your model is saying so. It is entirely depending on, you can also point it out to the basic scientist that this I observed, does it make sense to know? If the agreement is right, then only you can throw out the outliers. Okay, so outlier detection. So there are a lot of techniques. I will talk about few of them. One is jackknife residuals. So this is a long story. So here, what we do that, we have n points, just exclude the point I and recompute the estimate. So based on the n-1 observation, you get the estimates there and you define that one. Okay. Now you check that this quantity, predicted quantity minus the observed, is large or not. If it is large, then it is an outlier. And now the question is, how large is large? It depends on the context. So by doing this for repetition, each of these endpoints, you will get n values of this one and corresponding to check n outliers there. So you can check whether each of the point is outlier or not. Okay. So just looking at the epsilons, it is more difficult observations, or you cannot say something like that. So in some cases, it can pull the regression line close to them and they can conceal that status. So this is actually very problematic point, because from epsilon, this may not be revealed. Because of that, your straight line can be pulled towards that. So in Anscombe graph, someone told that the third graph was that, or that was because of this kind of problem is there. And variance of these jackknife residuals can be calculated like this one. So I must skip this one. And finally, you will do a lot of things here. We'll skip this one also. So the last one here in this topic is the Cook distance. So this is actually used to measure the influential observation. So this is the expression. I will not go into that detail, but bottom line is that you can get the Cook distance versus index or the half normal quantities. So you will see this kind of graphs. Now, these are the sum of the observation that can be think of the influential or outlier observation, because most of the points, so this is the Cook distance going on. Okay. Now, these are the very high distance, so they can be potential outlier or influential points. But again, you need to talk to the basic scientist or the scientists concerned who are familiar with the data and the basic understanding of the knowledge. They can only tell you that whether that point is actually influential point or not, and then you can only decide that whether to delete that data or not. But do not delete the data from yourself. Data is very important and very costly. Okay, now finally I came to some data examples that I wanted to explain to you. Okay, so that you have the feel what is going on. Any question up to this point? I will take only one here.
Sir, I have one question. We have assumed so many assumptions regarding the error, but those assumptions are not reflected even in our mathematical model.
I don't. So you are saying that we have assumed so many assumptions about the error.
Yes, errors. Yeah, but those are not reflected in the mathematical equations.
How? What do you mean by that?
I mean that if we don't assume those assumptions, also if we are estimating, if we are minimizing the ordinary least square error, then we will also get the values of beta naught and beta 1. Same.
No, there will be some problem. So for example, your one of the assumptions were expected value of error is equal to 0.
Yeah.
You mean that you can violate that one?
Yeah, yes.
Okay, let's check that. Okay, so if your epsilon is like, say, for example, alpha plus epsilon I star, right? You are talking about something like this, right?
So, sir, I am just saying if we have any data, sir, and if we do the ordinary least square, then we will get the values of beta naught and beta 1. Right. So whatever be the error, right? So whether we assume it, whether the error is are normally distributed or not, it will not write how the model will be altered.
No, I said that that's not exactly a point I did. That normality assumption is not required to get the estimates. Without normality assumption, you can still get the estimates.
But any other estimate, whether it's a homoscedasticity or of your expected value of errors, right? So again,
yeah. So when you interpret those results, suppose you are talking about the height versus weight. Okay. If the errors are not uncorrelated or not constant variance, so you will use that data, right? So, for example, the height weight example is actually used within the child development. So, whether you are aware or not, so say, for example, when I was there, Singapore, my son was born there. So, every time we go to the pediatrician, so they actually check what is the height of the child and what is the weight. Okay. So now, depending on that, they are checking that whether the child growth is going on or not. Now you say that this data has suffering from the non-constant variance and uncorrelated error. Now, the inference that will bring out of this, that will not be valid. Okay, if there is those kind of errors, then the health authorities will not allow your model to be used in the public sense, because you cannot use those models are not validated. It may work for this particular thing. The moment you apply for another data, it will not work there. Okay, so every time, and so for example, what I'm pointing out, suppose your epsilon is there, something like that. Either you have to make your model like, so here we have a so here epsilon, expectation value of epsilon is equal to actually alpha. So not 0, right? It is one of the violation. So now if you write that model here, alpha plus epsilon star, then you can add this alpha here and beta 1 x plus epsilon star, and now you can write this at a beta naught star plus beta 1. Here you can adjust this one, but not all the time you can adjust. And specifically for your non-constant variance, you will see that when you calculate the values of the R square, those are not valid. And when you are trying to predict something, those predictions will not be good at all. Does it make sense to you?
Yeah, yes.
Or I make you more confused?
Yeah. No, sir, thank you.
Okay. So statistics is actually difficult. Sometimes a lot of things are not clearly visible. The only thing you have to spend more and more time to get on these things. Okay, I'm running out of time. So let's go on the data of the height data example. So this was collected by one of the famous statistician Carl Pearson. So that's under whose name the Pearson correlation coefficient is there. This is the Carl Pearson that you are introduced by me right now. Okay, so it was 1893 to 1898, and it was about the 1375 mothers in UK under the age of 65 and one of their adult daughters who were the age of 18. Okay, and this was one of the historical examples to use of regression to study the inheritance of the height from the generation of the generation to generation, and the regression term is actually coined by that time from this kind of data. So it was said that the heights of the daughter was regressed from mother side towards the mean kind of thing. So there is another story, but sadly I do not have time to share with you. Okay, so this is the R code. So I will request all of you to download R. I think Professor Sairam already shared you the link to download R, basic R and R Studio, so that when we talk about the hands-on training, so that you can actually do something to feel about the whatever you have learned, and that will be very much helpful. So this is one of the data library in R. So if you this height, so if you do the head of height, so this will show you the data and how the things are going on. So this is data in inches, and this is the mother height, M height, and this is the daughter height. And if you write the summary of heights, this will give you the mean, first quartile, median, mean, third quartile, max. Okay, and this is the STR, that is the structure, and it will give you the what kind of variable. Both are numeric variable, 1375 observation, 2 variables are there, and some examples of these variables. So here I am going quickly. Do not worry about that. I will explain all the examples like this kind of data sets during the lab hours by hands-on. So for the sake of completeness, I will quickly go through all those things so that you can have some idea, because I have talked so much theoretical things, and now how you things can be applied in real data, that will give you a much more better picture. So we have talked about the scatter plots. We'll do the scatter plot here using the plot term. And this is the scatter plot. So this is the mother height and this is the daughter height. So again, now you have daughter height and mother height. What should be my X and what should be my Y? So typical thing is that what is the cause and what is the effect? Cause is the mother height and effect is the daughter height, in that sense, because from the mother height, we are trying to infer about the daughter height. So daughter height, we are inferring the kind of effect in a very loose sense, then it should be the Y, and that's why it is there. And when I'm talking about the mother height, the first thing that is the cause it should be in the X. And we can see there is a upward trend towards from the mother side. That means that if we expect mother, when the mother side is very high, we expect that daughter side to be very high. Okay, but there are a lot of portions which are not following that one. That's the beauty of real data analysis. Okay, so very quickly in our, just a minute, you can fit a regression line, but calling the term LM for linear model, the Y, the sign, like Y, the sign X, and then data. Okay, this is the term that you can see. So then I will get everything, results will be stored. This is a name, you can write height.lm or a DD or anything. This is a name, nothing fancy about that. So now you just write summary of height.lm. Then this is the final outcome. Okay, so this is very interesting, and this is the result that you expect for. So this is the formula, daughter height, that is my Y. This is M height, that is my X, and this is my data, height data. Okay, so this will give you the residuals. What is the minimum residuals? In this case, minus 7.39, and the first quartile is this, median is 0.036, third quartile is 1.49, and maximum value is this one. So minimum lies between -7 to 9. So that is the residual statistics here. And these are the estimated coefficient. The intercept, so model is like Y equal to beta naught plus beta 1 X. So this is my model. So this is the intercept here, and estimated intercept is 29.91, and this is the beta 1 here, and that is the M height. So this is my X M height. The coefficient of this one is beta 1, it is 0.54. And corresponding standard error of that we have the formula, it is calculated at 1.6 here, and this is 0.02. There is a p-value concept based on the p-value. This is called the p-value. Now, many of you will struggle with the p-value. So here, I told about that. Here, basically what we are doing a hypothesis testing. For this case, beta naught is equal to 0 against beta 1. Okay, so corresponding to this hypothesis, that means once I get all the estimates, I am checking whether beta is actually 0 or actually away from 0. Here, with that, we find that p-value is very, very small, and it is actually, though this quantity is saying that this p-value is lying between these two values. If it lies between 0.001 to 0.01, then we'll have only 2 star. And if it lies between this one, 1 star, similarly this one. Okay, so that means this is highly significant. Significant means we are rejecting this concept of beta naught equal to 0. That means we are saying that beta 1 not equal to 0, this is significant. Significant means that this value has some significant importance there, very loosely. Similarly, M height, which is estimated value 0.54, this is also significant. Corresponding, just you replace this one beta 1. This was beta 1, so this is beta 1. So you are saying that this is also significant, very, very small p-value. That means it makes sense. So there is a relationship between X and Y, and the corresponding beta 1 hat, that is a significant relationship on that. And here the R square, multiple R square value is 0.24. Okay. So that means that whatever variability we have in Y in the daughter side, based on the mother height, I am only able to explain 24% of the variability daughter side. That's not too good. Okay. Even so, even from this graph, you are sensing that there might be very good linear relationship, because a lot of things are there, and that is actually causing the problem, and we have ended up with the R square, which is not so good. Okay, and there are R square, there is no concept of, this is similarly. F statistics is there, and p-value of this model, so that model is significant, but what we expect the R square, it's not too good our purpose, even though we find the model is significant. Okay, there are few quick things. If you put the head of the fitted line, so these are the fitted observation. I'm just printing 6 of them, but you can print all of them. If you just remove this head, and if you just write this one, it will print all the n observation, or 1, 3, 7, 5 observation here. Similarly, head of residuals, you can get similar things. And residual standard error, sigma, you can get it here. And similarly, you can extract the coefficient of these like intercept. So these are the same coefficient that we already. So many things actually stored in height.lm, and you are trying to extract all those things. And if you want to round off, you can just use this command in R to get all those things. And the regression diagnostics there, you can plot height.lm. So you are getting this one. Now, these are the diagnostic plots. So one is residual versus fitted values, standardized residuals versus theoretical quantities, square root of the standardized versus fitted values, standardized residuals versus leverage, and quickly check this one. Okay, so first one is residual versus fitted, this one. What I expect here, as I told out, this is a line, and I expect that points are randomly distributed here. More or less, this graph is fine. So here we expect the scatter plot to be symmetric vertically along y-axis about 0. Okay, and it is used for the check assumption constant variance of errors. Okay, and normal QQ plot, I explained earlier. I explained that this should plot in a straight line, and here more or less it's fine. A little bit problem here, but practical purpose I can ignore that one. And where we expect the residual points follow the straight dashed line, and the scale location, here you also similar kind of things, horizontal line with equally spared points. Horizontal line with equally spared points, more or less it is fine. Okay, and this is to check homoscedasticity assumptions. And the last one, residual versus leverage, is used to identify the influential observation. And here we do not expect any pattern in the other three graphs above. Okay, so here you can observe there is a red line here. I will be giving, if there is some points here, then there is a chance that there is the influential points there, but at least of this graph, there is none. So I should not care about that. Okay, so finally, the fitted line here is the daughter height.
So what is leverage there? Leverage?
Sorry?
What is
Sorry?
leverage there? Leverage. Leverage in the graph, the fourth graph.
Yeah.
Residuals versus leverage. Leverage means here.
Leverage is calculated from the Cook distance.
Okay.
So, okay, so this is the, I mean, influential points. I have not mentioned probably, but you can check in any book to how to calculate the leverage. But this is actually for the checking of whether you have any influential points or the outliers. Okay, so this is the model that we have. Daughter height 29.9, 0.54 multiplied by mother height, and interpretation is that. So how do I interpret this is very important. So in general, if mother height increase 1 unit, that means 1 inch, and these are the constant, I will expect that daughter height will increase 0.54 inch. As simple as that. So this is the beauty of linear regression. Your interpretation you can actually do. So if I increase here, so for example, if I increase mother height from 50 to 51, that means you will have two regression lines. Say for example, y is equal to 29.92 plus 0.54 multiplied by 50, and another one will be like, so let's y1 and y2 is equal to 29.92 plus 54 multiplied by 51. Now you will cancel out, so 2 minus 1, if you consider 2 minus 1, then this will cancel out, and this will difference is 1. So the y2 minus y1 is basically becoming 0.54. That means again, I am repeating, if mother side increase from 1 unit, and that does not mean, so the interpretation of these things 50 to 51 is same as 70 to 71. So that means here 1 unit, doesn't matter which one. If the mother height increase 1 unit, I will expect on average, the daughter height will increase 0.54 unit. That's all. And if you have a nonlinear models, then this change will affect from where you are changing 1 unit, that exactly matter. And but here in this case, linear regression, that does not matter. Okay, so very quickly, I have only 1 minute left. How to attack the data analysis or model fitting problem. So you need to understand the research questions and understand the data very well, how the data is collected, and what type of design, study design is used, randomized. So you must be familiar with the randomized trial, at least with respect to COVID vaccine, you are aware of that. The third phase randomized trial, or whether it is observational data or prospective and retrospective. You can search internet because we do not have time to explain all those things here right now. And can you make any connections with the primary research question that you have and the data? The research question feasible. Sometimes you may have data, but the research question that you want to know is not feasible from your point of view or based on the data. Are there any secondary research questions or there or not? What are the potential sources of bias? This is a very big concept, and still we do not have time to explain all those things. So if the samples may not represent the target population, then it will not be a good one. So I'll give you a quick example. Suppose you are estimating average income. Suppose you include in your sample, say you have 100 samples, and in that sample there is one guy who is a billionaire, like his income in crores. Now, if 99 are very poor, and if you have one point like that, then your average income will be less. So that means give you a false information about the average income. So that means from where you are taking sample, that is not actually representative of the population because of that one point. So you need to think care of that, whether the sample is actually representative of the population or not. Otherwise, you will not be able to answer any question irrespective of regression model, any model. Are there any confounders? So what is confounder? Confounder is a variable that influence both dependent variable and independent variable, causing a spurious association. I do not have time, so this is another big concept. And whether you are dealing with the small data, then a lot of things will be problematic for you. And how to attack the problem? So you can first, at least for the linear regression, you do the scatter plot to start with, response versus input variables, see how the things are going on, fit the regression model or any other type of model, and interpret the outcome from the fitted models. Are the results are expected? This is very important. You need to consult with the domain expert whether the results are consistent with you. Only then you can think about the model is good or not. If not, what are the reasons behind the aberration from the expected results, and check the diagnostics for the model assumptions. And if there is some problem, try to correct all those problems. And as I always pointed out, quoting box, that all models are wrong, but some are useful. So your model might be one of the useful model. And how to use the predictive model in simple linear regression. So go with the research question, find the appropriate data, check the assumptions, fit the simple linear regression model, check the diagnostics. You have already done all those things. If everything is okay, finalize the model. And say, for example, we are talking about the Assam. What is the expected flood area in Assam? If you know the flood area, the government can take different preventive measures to stop all these kinds of flooded area and can save millions of lives. Now, if someone told that this year average monsoon rainfall will be 190 centimeters, typically the average monsoon is around 180 here in Assam, but whether it is above average, then if you fit your hypothetical model, so this is, I have do not have data. Let's consider the hypothetical model. Flood area is 500 plus this is the coefficient and average rainfall. Now, this is the fitted model that you have gone through after all this. And now you need to put this 190 here, and then you will get a flooded area in square kilometer. Okay. And then you can say that to the government, look, this is our model. If the model is correct, we'll have, and if the rainfall is around 190, we'll expect to have this amount of flooded area in Assam. So government, based on your data, based on your results, the government can take appropriate step. That's why as a statistician or data scientist, you are helping others, and that's exactly your job. So these are some references, introduction to linear regression model analysis, and this is by Montgomery, and of regression analysis. This is another good book. And for the R part, you can look these linear models with R. And with that, I will say thank you to all. So maybe I will take one or two questions and then I'll stop. So you do not have any other things today, right?
Yes, Palas.
Yeah.
So this is the last session. You can continue.
Okay, I will take one or two questions because I have another meeting after that.
Okay, sure.
Okay, so participants, if you have any questions, you can go ahead. I'll try to answer all of them.
So can you please once again tell how to calculate the values of beta naught and beta naught hat? And what is the difference between them?
Who is this one? So can you so that video on so that
Yes, sir.
I can see you. Otherwise, it is very difficult. The online, it looks like I'm talking to computer. Yeah. So what is the problem? Can you tell me again? So you are confusing the beta naught and beta 1 hat.
No, sir, no. Beta naught, yeah, beta naught hat.
Beta naught and beta hat. So these are the terminologies. Beta naught and beta naught hat is terminologies. Okay. So when you write in the model y equal to beta naught plus beta 1x plus epsilon, that is the parameter. Okay. Now at this point, I do not know what is the value of beta naught. That is a parameter, right?
Yes.
Okay. Now you do the derivative. You will have some expression of beta naught.
Yes.
Okay. The moment you in that expression you put all the values of xi, yi, x bar, yi bar, whatever you will get a value. Say for example that value is 1.5. I will call that value of beta naught 1.5 as a beta naught hat.
So why we can't?
Why?
Why can't we say that only beta naught? Why we are bringing the concept of beta naught hat? That I want to know.
No, suppose if you want to calculate the expectation of beta naught hat, you can't write expectation of beta, right? So expect beta is a constant. The moment you put beta naught hat, that's become a variable. Is it clear to you or it's still confusing?
No, sir. Then yes, it's okay. I will try some more later.
No. So beta naught is a function of y and x. Beta naught hat is a function of y and x. Beta itself is a constant. Those two things are different. Okay.
Okay, sir. Okay.
So you need to study a lot. So the
Sir,
yes.
does this mean that there would be a single value of beta naught?
Can you open your camera so that we have a better feel of the discussion?
Whereas we can have a range of the beta naught hat. I mean, there would be a distribution of the beta naught hat, but the value of beta naught would be a unique value selected from the distribution of beta naught hat. Is this the case, sir?
When you are talking about the beta naught hat, there is a distribution, and based on your data, you are having some values. Okay, and that's why we, because there is a distribution, we have to calculate the variance also. That's why we exactly calculate the variance of beta, both of the parameter beta naught hat and beta 1 hat.
All right. So does this mean that there would be a unique value of beta naught, unique value, which our model or whichever software will give us that this is the value of beta naught? Say, for example, 20.59.
Think about the linear regression model, simple linear regression model, and if you use the least square estimate, yes, this is the unique value.
Right.
But if you use something else, it will not be unique.
Okay. Thank you, sir.
Excuse me, sir.
Yes, go ahead, please.
Yes, I'm very much new to statistics, sir.
If possible, open. Yeah, go ahead.
Sir, I had a confusion. Like there was an assumption that there should not be relationship between the error terms for regression.
Say that again. There should not be.
There should not be a relationship between the errors.
Yeah, that means the error are uncorrelated.
Okay, sir. So is it the same like the multicollinearity, or multicollinearity is something different, sir?
No, multicollinearity is something else. Because this is a very short course, we will not have, there are a lot of, so linear regression kind of you are a full semester course and you are learning in a 2 lectures. So
yes.
you can, so multicollinearity means that when you are multiple linear regression, you have x1, x2, x3. Okay. So these are the input variables. The multicollinearity means that whether those variables are related to each other or not.
Okay,
Whether
sir,
x1 and x2, when they are highly correlated, we call that there is a problem of multicollinearity. And then when you estimate the parameters, those will not be stable.
Okay, we don't use statistics often, sir. So
Yeah, it's
I
fine.
yeah.
So if all of them use statistics, what will be my job? I will be jobless.
True, sir. Thank you, sir. Thank you.
You're always welcome. Any other question? So someone writing something, I don't know how to check that one. Let me stop this one.
There is a question in the chat.
Yeah. I am not able to. Where is the chat? Yeah.
Sir.
Yeah, let me check that one. Yeah, sir. Algorithm applied to the real life situation, as every year there are floods in India from a couple of years from now. If so, has been the. Okay, this is an interesting question. This is about the application. So yes, you can apply the models, but the problem is that you need to have a right kind of data. The example I showed that is actually hypothetical data. Hypothetical means there is no actual data, at least to me. So this is just an example. Yes, you can. If you can get the data, that will be useful. And not only that, this is a very simplistic situation. We are only considering one variable here, but there are a lot of other factors, and some factors is not only like human behavior also. Suppose you have a data and somebody in their area in the bank of Brahmaputra river, somebody do something, those data will not be to you, and those will be affected to your model, all those things. So these are bigger problems. We have a multivariate problem. I am just talking about a chunk of things, very simplistic situation. But if you actually apply or actually try to find out the predictive modeling about the flood area, so you need to have lots of data, including the satellite image, using the how the things are going on, what are the rainfalls, and what are the temperatures, what should be the position of the clouds, and the people behavior, migration, how much amount of water discharge from the other dam surrounding area, what are the bigger movements like the agricultural aspect, how much water already taken from the systems, whether soil erosion. So you can add so many factors you can. So these are very much complex problem. The thing that I give you are like peanuts of the entire gigantic problem that you can think of. Yes, someone is asking some question.
Sir.
Yes.
Is it audible, sir?
Yeah, go ahead, please.
So actually, I am having one model, sir, a hydrological model. It has been fitted with a linear regression, root mean square error, and then residual square error. So is it possible we can derive this and we can fit it to that existing models, sir? Linear regression models?
I don't get your question exactly. So you have a data and you are fitting linear regression model. Is that correct?
Yes, sir. Yes, sir, with the existing models, sir. That is already derived softwares, like softwares I'm saying, sir.
I mean, when you ask this question, what is your outcome variable?
That is, I need that is regressions, like show the values, no, sir. That is r square is equal to 1.
No.
Point.
First, talking about what is the y variable, what is the x variable here?
That is rainfall. That is rainfall and runoff, sir.
No, last one I am not getting.
Rainfall and flood, sir.
Rainfall and flood. Which one is y? Flood is y?
Yes, sir.
Okay. And the same example.
Okay. Yes, sir. Excess rainfall, sir.
Okay, then?
Then actually the model is already developed, sir. So whether you're showing regressions, no, sir, whether we can that is derive our own regression or we have to work with.
You need to speak slowly. I am totally not able to understand anything out of your voice.
Model is already a well-developed model, sir.
You have developed the model.
Yes, sir. Whether we can develop our own model and we can fit into it, or we have to, because whatever the models are there, it's already a black box model only. But we want to know whether what is really happening inside the models, whether this regressions can be applied there. I'm asking in point of application point of view, sir.
Yeah, I mean, you can apply the regression. So it is very difficult. I should not, as a statistician, if I do not see the data, I will not recommend what can we do. But you can try the regression. There is no harm in that.
Okay, sir.
But to see, I mean, exactly, so we need to see. I mean, it's not straightforward. Just someone give you the Excel file and you just fit the regression. I am extremely strongly against with that idea, because
Yes, sir.
what kind of data you have, that will have a different interpretation. Okay.
Yes, sir. Because no, you showed the case study regarding rainfall and flood. So I am also dealing with the same thing.
Yes,
But
definitely
it is,
you can apply.
it is a developed model, because whatever input we will give, it will give the output and regression there. But we don't know what is happening inside, in between that process. That
What
is,
kind of model you have used?
sir, that is,
You use regression model.
yes, sir. There are a lot of options, sir.
What software you are using?
That is HMS, sir. HMS.
But that should give you all the information. Like, so it is a basic things, and you should get all the information. And the way I have presented, you should check all the assumptions and the validity, and try to predict the in-samples. That means you have a samples, and you try to forecast each of the in-sample observation, and check that whether how the model is working. If it is working fine, then it's good.
Okay, sir. Fine, sir. Yeah, okay, sir. Thank you, sir.
Anything else? Any other question? Okay, so if there is no other questions, I'll stop you there here. And tomorrow we'll talk about the multiple linear regression and logistic regression. But again, the time is very short for 1.5 hours to cover all those things. But we'll see what we can cover from our end. Thank you very much. Over to you, Asukda.
Yeah, thank